we define reflection as the bouncing of light from a surface. Refraction, we are defining as the bending of light, from one surface or from one medium to another medium of different optical densities. So when we talk about refraction, it is about bending of light as it moves from one medium to another of different optical densities, or the same refraction, or we define refraction as a change in the speed of light as it moves from one medium into another medium of different optical densities. So for refraction, it's about bending, but the light must travel from one medium into another. And these two different media must have different optical density. There is the use of the word optical density because the two media must be such that one, it allows light to pass through. Because when light passes through an opaque material, you will not see the light when you are to view it from the end. So to be sure the light really has bent, light must be able to pass through the material. And if the two have different densities, then we can say refraction would happen. Or when light moves from two different media whose densities are not the same, the speed of light would certainly change. Okay, so this is about refraction. Now what it means is that if we have two materials, material A and material B, and the two materials have the same density, rho of A is equal to rho of B, there will be no refraction. The light, part of the light will not bend because these two materials have the same density. For refraction to occur, then the density of A must either be great or less than density of B. They must have different densities. Please, are we okay?
Yes, please.
Kenneth, are you okay? All right, so let's look at what happens when light moves from a less dense medium into a more dense medium and vice versa. These are two materials, A and B. Now the density of A is greater than density of B. So if density of A is greater than density of B, then we can take this example. This material can be glass, and this material can be air. So light is being propagated from glass to air. When we draw a normal to the boundary, the normal is always an imaginary line which is perpendicular to the two media. Okay. So we've drawn a normal. Now when I incident light here, a ray is indicated by an arrow. Because this is the incident ray, the angle between the normal and the incident ray, this is known as what? What name do we give to the angle between the normal and the incident ray? Yes.
Angle of incidence.
Good. So that is the angle of incidence. So I is the angle of incidence. Now, if row of A, row of B, we call this as the boundary or the interface separating the two media. Now, if light travels from, whenever light travels from a denser medium into a less dense medium, the path of the light is refracted away from the normal. So the speed of the light changes, but the deviation it will be refracted away from the normal. So this ray becomes what we call refracted ray. And the angle between the normal and the refracted ray, this angle is known as angle of refraction. R is equal to angle of refraction. So the concept length is that when light ray moves from a dense medium to a rare medium. This rare medium also means less dense to a rare medium or less dense medium. The refracted ray bends away from the normal. So in this case, if we compare the angle of incidence to the angle of refraction, which one is greater? Yes. When we compare the angle of refraction to the angle of incidence, which one will be greater here? Oh, a quick view. If yes, Josephine.
This is the angle of refraction.
So the angle of refraction R is greater than the angle of incidence. So R is greater than I. Whenever light travel from a denser medium into a less dense medium. Now, if the light is moving from a less dense medium into a denser medium, example, air to glass, normal. There's a normal end. So if light would have to travel from air to glass, and here rho of air is greater than rho of is less than rho of glass. What do you think will happen to the refracted ray? What will happen in this situation? Will the refracted ray bend away from the normal or towards the normal?
To bend towards the normal.
So here, the refracted ray would bend towards the normal. So let's compare. This is the angle of incidence, I. This is the angle of refraction, R. When you compare the two, what will you say? Adra, what will you say about the angle of incidence and the angle of refraction?
The angle of incidence is greater than the angle of refraction.
So here, I is greater than R, or R is less than I. So whenever light ray travels from a less dense medium into a denser medium, the refracted ray bends towards the normal. Bends towards the normal. Now, when we extend the original direction of the incident ray, we can determine how much the incident ray has been deviated from its original path. What I'm saying is that this is how the incident ray is supposed to travel. Now, due to the fact that the ray is moving from air to glass, its path has been changed to this part. So this becomes the refracted ray. So if we want to determine how much the incident ray is deviated from its original path, this becomes the angle. And this angle, we call this as the angle of deviation. Angle of deviation. So we could deduce, but when you look at what is on the board, the angle of incidence must be equal to this whole angle. Must be equal to this whole angle. It must be equal to this whole angle. Because vertically opposite angle. So I it's supposed to be equal to angle of refraction R plus the angle of deviation. So here you must define where I equals angle of incidence R equals angle of refraction, and sigma equals angle of deviation. So sigma is equal to I minus R. So angle of deviation is equal to angle of incidence minus the angle of refraction. Please, are we okay? Are we okay?
Yes, sir.
And don't forget this relation in refraction. If you recall, for mirrors, plain mirrors, we deduce a similar relation. This is the normal. And when you incident light onto the surface of the mirror, mirrors reflect. So this will be reflected. And the angle of incidence I is equal to the angle of reflection R. Now for mirrors, when you look at this ray, the incident ray is supposed to move straight. But its path is deviated to this side. So if we want to measure how much the original incident ray's path is deviated, as I said, it's supposed to go straight. Now it's been deviated to this direction. So this is how much the ray is deviated. So for mirrors, angle of deviation sigma is equal to, look at something. This whole angle here is supposed to be 180. Okay, we are looking for this angle. So if this is equal to 180, then when we subtract these two angles from 180, we'll get what is left. Please, isn't it? Are you with me?
Yes, please.
So if we subtract these two angles from 180, because the whole angle is 180, we get the deviation. So 180 minus, now in mirrors, angle of incidence equals angle of reflection. So this can be 2I or 2R. So the angle of deviation is equal to 180 minus 2I or 180 minus 2R. This is how to determine angle of deviation in mirrors. But when it comes to refraction, this is how to calculate for the angle of deviation. Is the angle of incidence minus the angle of refraction. Please, any question? Any question? All right, no question. Okay, then let's continue. Now let's look at laws of refraction. Laws of refraction. Can I clean the board?
Yes, please.
Laws of refraction. Before we look at laws of refraction, let's discuss Laws of reflection. What are the two main laws of reflection? Adua, give me one of the laws of reflection.
The angle of incidence equal to the angle of reflection.
So angle of incidence equals the angle of reflection. And what's the other one?
The reflected ray, the normal and the incidence angle at the point of incidence all are on the same plane.
Okay. So under reflection, we have similar laws. Under refraction of light. So when you draw, you have the boundary between the two media. This is the normal, which is always perpendicular to the surface. So when you incident a light ray here, you have the angle of incidence and the ray, the path of the ray, either deviates if it is air to glass, less dense, or rare medium to a dense medium. The deviation is towards the normal. So the first law is that the incident ray the refracted ray, the normal at the point of incidence all lie in the same plane. This is the first law of refraction. So laws of refraction. Then the second law. Who are those gone? I have Ajoa, Donchua, Hendricks, Yanis, and Josephine. Kenneth is gone. And Equia. Equia is back. The second law. The second law says that whenever light travels from one medium into another, whether from less dense to denser medium or denser medium to less dense medium, when you take the ratio of the sine of the angle of incidence, so sine of I to the sine of the angle of refraction, this must give you a constant value. So whenever light travels from one medium to another, maybe from less dense or rare medium to denser medium, or denser medium to rare medium, no matter the two different media, what matters is that they should have different densities. If you take the ratio of the sine of the angle of incidence to the sine of the angle of refraction, this must give you a constant value. And this constant value is what we refer to as the refractive index. Refractive index. This law, this ratio of the sine of the angle of incidence to the sine of the angle of refraction is what we call as Snell's law. Snell's law. It was named after a Danish physicist by name Willebrord Snell. Willebrord Snell. So what is Snell's law? Snell's law says that a aqueous network isn't stable. Snell's law says that when light or whenever light travels from one medium into another, of different optical densities, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. That is Snell's law. So for any given two media of different optical densities, another way of stating the law, for any given two given media of different optical densities, the sine of the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. For any two given media of different optical densities, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Please, are we okay? Class, are we okay? Are we there?
Yes, please.
So these are the two main laws of refraction. These are the two main laws of refraction. Now, what does the law mean? Snell's law, what does it mean? I said the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. And this constant is termed as the refractive index of the material. Refractive index. Now, what is refractive index? The refractive index of a material is the measure of the material's ability to deviate light. The refractive index of a material is the measure of the material's ability to deviate light. The measure of the material's ability to deviate light or bend. To deviate or bend light. We usually compare this measure of the material's ability to deviate light to air. So the refractive index of glass is equal to 1.5, meaning that glass can bend light 1.5 times than air. So the refractive index of glass is 1.5, meaning that glass can bend light 1.5 times than air. The refractive index of water is 1.333, meaning that water can bend light 1.33 times than air. Please, are we okay? Janice, are you okay?
Yes, please.
So we are always comparing how the material can bend light to air. How the materials can bend light to air. All right, so let's go into this refractive index thing and then talk more about it. Attendance is poor. Let me check attendance. So we have Adwa, Equia, Dontua, Eliana Boateng, Eliana. Hello, Eliana.
Mr. Dia.
Who are you? I don't know you.
Visitor Benoa.
Ah. Okay. All right. So let's look at absolute refractive index. In fact, we can discuss 3 different forms of refractive index. I have already explained to you what refractive index is? The refractive index of a material is the measure of the material's ability to deviate the path of light. So the refractive index of glass is 1.5, meaning that glass can deviate light or bend light 1.5 times can be done by air. Refractive index of water is 1.33, meaning that water can bend light 1.33 times, okay, as air. We can express refractive index in three different forms. One, we can talk about absolute refractive index. Two, we can also talk about reversed refractive index. Then lastly, we can talk about relative refractive index. The same refractive index. So now what is absolute refractive index? The absolute refractive index of a material is the actual refractive index of the material. Is the real or the actual refractive index of the material. You see, I earlier said that the refractive index of water is 1.33. The refractive index of glass is 1.50. These values are the real or the actual refractive index of the two different materials. The real or actual refractive index of a material. So whenever we talk about absolute refractive index, we are comparing how the material bends or deviates the path of light when the light is traveling from air to the material. So for absolute refractive index of a material, light must travel from air to the material. So for absolute refractive index, the first medium must be air. So this is glass or water. This is air, the normal. Light traveling from air to the material, and because water is denser than air, how will the light deviate? How will the light deviate? Yes. Answer, how will the light deviate?
Please, towards the normal.
It will bend towards the normal. Okay. So When I take from Snell, when I take the ratio of the sine of the angle of incidence from Snell's law, sine I over sine R, this ratio would give me the absolute or real or actual refractive index of water. And it is absolute or real because the light is moving from air to the water. If I should take it the other way around, now this is water, this is air, and the light is moving from air to glass. I R. The light is moving from water to air. When I take this ratio, sine I over sine R, this ratio is not equal to the absolute refractive index. Why isn't it absolute refractive index? Because the light is moving from water to air. For absolute, it should be from air. The first medium must be air. Please, is that okay?
Yes, please.
So, and this will actually be the reverse refractive index. It will be the reverse refractive index. Please, let me pick this call and get back to you. Hello. Hello. Are we
Hi.
there?
Yes.
Okay. Then real or absolute refractive index can be expressed in different forms. Here we are expressing it in terms of the angle of incidence and the angle of refraction. It can also be expressed in other different ways. So let's quickly go through the possible ways of expressing absolute refractive index. One, we are saying that the absolute refractive index mu or n. Please, these are the symbols that are used to represent absolute refractive index. You can use mu. This U like thing is a Greek letter. You can use mu or nu. The first one looks like U. The second one also looks like M. These are words and letters that are used to represent absolute refractive index. So we are expressing absolute refractive index mu or nu in terms of the ratio of the sine of the angle of incidence to the sine of the angle of refraction. Another way we can also represent absolute refractive index is we can take it as a speed of light in air, the ratio of the speed of light in air to the speed of light in a medium. So mu is equal to C over V, where C is equal to speed of light in air. V equals speed of light in a medium. A medium. Light travels from the speed of light in air is greater than speed of light in any other medium. It's even the same as we human beings. Imagine yourself running through air and then running through water. Which one is more difficult? Kenneth? Which one is more difficult?
The please running in water.
Yes. So in the same way, light, the speed of light in air is greater than the speed of light in water or any other medium. So absolute refractive index can also be expressed as this, the ratio of the speed of light in air to the speed of light in any medium. Andres, is that okay?
Yes, please.
Okay. Then another way of expressing, so we've talked about one. This is in terms of angle of deviation in medium one, in air to the other medium. So this is the second point. The third way of expressing absolute refractive index is this. In fact, speed or velocity of light is directly proportional to the wavelength, lambda, wavelength of light. You understand wavelength as we move on. So if speed of light is great in air, it means the speed of wavelength of light in air is also great or large. So we can express absolute refractive index also in terms of wavelength, and that is wavelength of light in air over wavelength of light in a material or medium. So absolute refractive index equals lambda in air. There's a symbol for wavelength. Lambda in air over lambda in a medium. So these are different ways of expressing absolute refractive index. Either you express it as the angle of deviation, sine of the angle of incidence using angles, sine I over sine R, or speed of light in air over speed of light in a medium. Josephine, mute yourself. Or wavelength of light in air over wavelength of light in a medium. Now the absolute refractive index of a material is always greater than 1. So absolute refractive index of a material is always greater than 1. I want somebody to explain to us why. Why do you think? Look at this example. Okay, so I said the absolute refractive index of water is 1.33. Absolute refractive index of glass is 1.5. Why do you think the absolute refractive index of a material is always greater than 1? Can somebody explain? This is free will. Equia doma. Why is the absolute refractive index of a material greater than 1? Equiadoma, are you there?
Was always always the
Pardon?
we said you're always the speed in A is greater than the speed in any other medium. So the numerator will always be greater than the denominator, which will always give us a number greater than 1.
And so you are right, but you are talking for only 1. Don't forget, I gave you 3 different ways of representing absolute refractive index. So when you look at what we've discussed, the first condition for absolute refractive index is that the ray must move from air to any other medium. So if you take the first expression of absolute refractive index, okay, we are looking at sine I over sine R. When you draw, light moving from air to a denser medium, you realize that I is greater than R. So if I is greater than R, if you take sine of I, ratio of the sine of R, I to sine of R, because the numerator angle is greater than the denominator, when you divide this by this, it should be greater than 1. If you take the second, which you spoke about, speed of light in air is always greater than speed of light in any medium, V. So because mu or n is a ratio of C over V, the numerator is greater than the denominator. So when you divide, you have greater than 1. Then the last one, wavelength of light in air is greater than wavelength of light in a medium. Don't forget, I said for wavelength, velocity of light is directly proportional to wavelength. So if the wavelength, speed of light in air is greater than the speed of light in any other medium, then it implies that the wavelength of light in air would also be greater than the wavelength of light in any other medium. So in this case too, when you take the ratio, because the numerator is greater than the denominator, you have a whole value which is greater than 1. This is the reason why absolute refractive index is always greater than 1. Please, are we okay? Are we okay? Okay. One thing which does not change whenever light has to move from one medium into another medium is the frequency of light. Are we listening? One thing which does not change when light moves from one medium into another medium is the frequency of light. So take note that frequency of light does not change from one medium into another medium. Velocity of light will change. Wavelength of light will change. But the frequency of light from one medium into another medium is always the same. All right. So, Andre,
Yeah.
tell me what I just said. What did I say?
It has been said the frequency of the light must change.
Come again.
The frequency of the light must change.
Must change.
Yes.
Andre, that's not what I said though. Okay, let me pick it from Adwa Asante. Adwa, what did I say?
This is said the frequency of light does not change when it's traveling from one medium to another.
Andre, maybe you did not hear me well. Okay.
Yes, please.
So I said one thing which does not change when light moves from one medium into another medium is the frequency of light. Wavelength will change. The speed will change. Of course, when speed changes, certainly wavelength must also change. But for frequency, it does not change from one medium into another medium. All right, that's what I said.
Yes, please.
Okay, so let's solve a question, and I'm reading. Are you ready? Are you ready to write?
Yes.
Yes, please.
All right. Find the speed of light. Find the speed of light of wavelength. Lambda is equal to 780 nanometer in air. So wavelength is equal to 780 nanometer in air. So this is the wavelength of light in air. So find the speed of light of wavelength 780 nanometer in air in a medium of refractive index 1.55. So we are looking for the wavelength of the material in a given medium. If the medium has a refractive index equal to 1.55. So once you are looking for the wavelength of the light in a given medium, then it means the light is moving from air to the medium. So this value of refractive index given is absolute refractive index. Why is it absolute? Absolute because the light is moving from air to a medium. So find the speed of light. Oh, we are looking for the speed of light. We are looking for find the speed of light of wavelength 780 nanometer in air in a medium of refractive index 1.5, meaning we are looking for the speed of light in a medium whose wavelength in air is 780 and the absolute refractive index is also 1.55. So B, question B, what is the wavelength of this light in the given medium? The B question is that, what is the wavelength of this light in a given medium? Please give it a try for about 2-3 minutes. Then we'll look at it generally. I'm giving you 3 minutes to just try. (780 nanometer) when the material has refractive index of 1.55. So absolute refractive index can be expressed in 2 different forms. One, speed of light in air divided by speed of light in a medium. This is what we are looking for. We are looking for V. Now, C is constant. Speed of light in air is 3.0 times 10 to the power 8 meter per second. So once we have this constant value and n, we can find the velocity speed of light in a medium. So when you make V the subject, you have C over n, which is equal to 3 times 10 to the power 8 divided by 1.55. Just divide 3 by 1.55 for me, and then give me the answer. Just 3 divided by 1.55. Yes, what have we had?
1.935.
So 1.935 times 10 to the power 8 meter per second. This is the velocity of speed of light in a medium. Please, how many of you got this? How many of you got this? Josephine had it. Let me check.
Mr. Dear, please I have a question.
Ask your question.
Mr. Dear, so the 780 nanometer, the question, you use it for anything.
We can also use it in a different way, and that's what I'm coming to find the same problem. Okay. And let's see it. You see, the same speed, absolute refractive index is either C over V, which is also equal to lambda in air over lambda in medium. Okay. So this 780 is what I have. I can use N is equal to lambda in air all right, lambda in air to find lambda in a medium. Because I know this, I can find this. So 1.55 is equal to 780 nanometer over wavelength in a medium. When I make this the subject, wavelength of light in a medium is equal to 780 over 1.55. So divide 780 by 1.55. Or even if you don't divide, is that you had what?
503.2.
503.2. Okay, is that correct?
Yes, please.
Good. So look at something. It means that if N is equal to C over V and is also equal to lambda in air over lambda in a medium, I can just say that C over V is equal to lambda in air over lambda in a medium. So that, let me change the marker. Because they are all equal to refractive index. Because they are all equal to refractive index N, I have found this. This is given to me as 780 nanometer. I've also found the denominator as 503.2. I have the numerator as 3 times 10 to the power 8 divided by V. Can't I make V the subject from here? So V would be equal to 3 times 10 to the power 8 times 503.2 divided by 780. So just maintain 10 to the power 8, multiply 3 by 503.2, and then divided by 780. Maintain 10 to the power 8. Let me see what you have. So 3 times 503.2 When you finish, divide by 780. Aren't we getting the same answer? We have V is equal to 1.935 times 10 to the power 8 meter per second. So, okay, this is another way we can use lambda to find whatever we are looking for. Is that okay? Okay, is that okay?
Yes. Yes.
Please, class, are we all okay? Or if you need some clarification, let me know. Okay, then try this. I want to see how you can, without my assistant, how you can also answer this question, a similar question. A one-color light beam, of frequency, one color light beam of frequency 6.0 times 10 to the power 14 hertz. A one color light beam of frequency 6.0 times 10 to the power 14 hertz crosses from air into transparent material, passes from air into a transparent material where its wavelength is measured to be 300 nanometer. Where its wavelength is measured to be 300 nanometer. What is the index of refraction of the material? What is the index of refraction of the material? So please give it a try, 5 minutes. I'll come to you, back to you in 5 minutes time. All the best.
Sir,
With,
please, I'm a maths class.
and this is physics class. So listen, a monochromatic light beam of frequency. So we are told that the light has a frequency of 6.0 times 10 to the power 14 hertz. This crosses from air into a transparent material. So from air to a material. So we are talking about absolute refractive index, where its wavelength is measured to, please listen, this crosses from air into a transparent material, where its wavelength is measured to be 300 nanometer. Where its wavelength is measured to be, what does this value refer to? What does this value refer to? Where its wavelength is measured to be 300 nanometer? Yes. This 300 nanometer. What does it refer to? Because
Sir,
you need to.
Sir, please, the wavelength of light in A.
Don't you all listen to this thing again? A one color light of frequency 3 times 10 to the power 14 hertz crosses from air into a transparent material. Crosses from air into a transparent material where its wavelength is measured to be 300 nanometer. What does it refer to? Where its wavelength is measured to be 300 nanometer. What does this value refer to? Yes, I'm waiting for somebody to tell me. Hey, nobody.
The wavelength of the
Pardon?
transparent.
So wavelength of light in the transparent material. It crosses from air into a transparent material where its wavelength is measured to be. So within the transparent material, its wavelength is measured to be 300. Okay. So this 300 nanometer refers to the wavelength of the light in the transparent material. What is the index of refraction of the material? So we are looking for the refractive index. But here, because from air to transparent material, specifically, we are looking for the absolute refractive index. Okay, now absolute refractive index is wavelength of light in air over wavelength of light in a material. So we have the denominator. We don't have the numerator to find nu. What do we have? We have frequency. But frequency of light does not change from one material into another. Now, velocity of light in any material, V is equal to F times lambda. Velocity of light in any material is equal to F times lambda. And F is equal to V over lambda. Meaning that if I'm talking about velocity of light in air, C must be equal to F times wavelength of light in air. If I'm talking about velocity of light in a medium, V must also be frequency of light times wavelength of light in a medium or material. Equation 1, equation 2. This has to do with air. This has to do with velocity of light in a material. So air and then material. Josephine.
Mr. Edia, please, can you go over again?
Okay. So look at how step by step I want to solve this question. I'm cleaning the whole thing. We are to look for the refractive index, absolute for air to transparent material, the absolute refractive index of a material. N can be wavelength of light in air over wavelength of light in a medium. This can also be velocity of sound, light in air over velocity of light in a medium. Now, what do we have? we have wavelength of light in a material. C is also constant. We don't have this, we don't have that, right? Now, generally, velocity of light is given by frequency times wavelength. So whether in air or in a medium, if it is in air, then velocity of light in air, which is C, is equal to frequency of light times wavelength of light in air, because this is about air. Then if in another material, medium or material, V is equal to frequency of light times wavelength of light in a medium or material. This is material. One thing we know for sure is that frequency of light does not change from material to material. So in equation 1, if we make F the subject, we have F being equal to C over wavelength of light in air. In equation 2, if we make F the subject, we have F is equal to V over lambda on over this. Now, knowing that frequency of light is always constant, it doesn't change from material to material, I can equate this to this because F here are the same. So C over lambda in air is equal to V over lambda in medium. What do I have? The question gave me C and this. So the best way is that, look at something. We are looking for, okay, we are looking for air in order to use this. Okay, but the easy way out is that since velocity of sound in air C is equal to frequency times wavelength in air, we can use this. We can use this and this to find this. And that is even simpler than going through what I'm even doing. Okay. So velocity of sound in air is constant. 3 times 10 to the power 8 is equal to frequency of light is equal to 6 times 10 to the power 14. This times wavelength of light in air. When you make lambda the subject, you have 3 times 10 to the power 8 over 6 times 10 to the power 14. This is equal to 0.5 times 10 to the power 8 minus 14, which is minus 6. And so it means that the wavelength of light will be 0.5. So 1, 2, 3. So I will have 500 nanometer. That's the wavelength of light in air. So getting this, we can use N equal to lambda in air over lambda in medium. Lambda in air, we have 500 nanometer. Lambda in medium, we're given 300. So this is equal to 1.667. Then the next question demands that we find the velocity of sound. What is the index of? I'm coming. Is it 2-in-1 question? Okay, so a one color light beam of frequency this crosses from air into a transparent material where its wavelength is measured to. What is the index of refraction of the material? Oh, okay. So it's even one question. I even thought we are to find the velocity of light in the material. So if there is a question on velocity of light in a material, look at it. F does not vary in air and then in a medium. So when we equate this to this, we have C over wavelength of light in air equal to V over this. So here we only make V the subject. If we are to find speed of light in the transparent material, P will be equal to C times lambda in the medium over lambda in air. And C is constant, 3.0 times 10 to the power 8. Lambda in a medium is given to us 300 nanometer. And we found lambda in air to be 500 nanometer. So we can easily find the speed of light in the material. So this is how you must go about this question. It's not so difficult, but you actually need to think through, have an experience. So please, what I want you to do is that right after the class, okay, or spend time today, tomorrow to go over what the two questions we have solved, or the notes on absolute refractive index. Absolute refractive index. But let me come back to my question. Tomorrow, what do we do? I said we have John Wesley.